Oh, sorry, I just said my whole answer, but I was on.
Yeah,
Um,
did you figure it, or is it what a geometric or optical
yeah.
isomer?
I said it was an optical isomer, and there were two optical isomers because there's one chiral center.
Very good.
Um,
That's a chiral carbon.
yeah.
Where do you find the chiral carbon to them?
It's the third carbon along that's bonded to the hydrogen, the carbonyl group, the nitrile group, and then the CI.
Ah, this is the one, right? Okay. So it's an
Yeah.
optical isomer. Okay. So you scored something, right? Okay. Optical isomer.
Is the geometric one this trans and EZ one?
Very good. Cis trans or uh, and yeah, cis trans isomerism, cis and trans isomerism. So it is there for alkenes, right?
Yeah.
Okay. Um, okay, now you have scored another one. You have identified the functional group. There's a carbonyl carbon, CN and OH. And the next part, what they are asking here, they ask mechanisms and equations are not required, right? So you must mention the, for example, the compound is here, right? Now, what sort of a reaction? For example, you can make mainly different type of reactions for nitrile group, for OH group, for carbon and carbon, right? What are the type of reactions? Nitrile carbon, CN. What do you think?
Um, well, potassium cyanide reaction.
Potassium cyanide. Okay. Now, for example, a carbon and carbon. If you add the lithium aluminum hydroxide, what will happen? If you add lithium
Um,
aluminum hydroxide, what will happen to this carbon and carbon?
I'm not sure.
It will get
I know
opened
that
up.
if you a nitrile, then it will turn into an amine.
Okay, so what sort of a reaction? Very good. So it means you are telling this can be converted into CH2 NH2. So what is happened here? What do you add here?
Um, the lithium aluminum hydroxide
What are the conditions?
or hydrogen and a platinum catalyst.
Very good. H2 platinum palladium, platinum or palladium catalyst. What has happened here now? Is it oxidation or reduction or what?
Um, I'm not sure.
Hydrogen has been added up, right?
Yeah. Oh, so
Yeah,
oxidation.
it has been added up. Hydrogen added, so it is an addition reaction. What else can you tell? It is oxidation or reduction.
Um,
Yeah. What has happened to the oxidation number of carbon? It has been reduced, right? When hydrogen is connected.
right.
Yeah, it has been reduced. Reduced. It's an addition reaction, it is reduced. What about here? When you are lithium aluminum hydroxide for this carbon and carbon, what is happening here? So this reaction you must memorize, right? There are few things you must remember. Huh?
Okay.
What is the product?
Mm, I'm not sure because I only learned about the lithium aluminum.
It becomes an alcohol, right? Carbonyl carbon is becoming an alcohol. It is a reduction, again. reduction reaction. Okay.
Yeah.
So these things you must remember, right? So otherwise you can't answer. Okay. Uh, so you can talk about another reaction. Now here what is happening? You have an alcohol group. What are the reaction of alcohol group? What can you convert this into?
Acid.
Yeah, right. What are the reagents? What are the oxidizing agents?
Oh, I always have a hard time remembering these.
These things you must remember, right? One thing is H plus manganate, right? MnO4. O H plus dichromate, H2Cr2O7. These are reducing agents, right? So as you said before, an alcohol is correctly converted into carboxo double OH, right? Now these things you must remember, right? But let's see how much marks you are losing here. 6 marks. So about 3 marks you can definitely score, right? You are scored. But other marks cannot be scored without you should know the reactions, right? Organic chemistry. You must keep that in mind, right? Okay, now I will erase this. Now you must answer it and send me the answer. Can you do it? Let's see whether you can remember this. Answer the question now. And you must draw the optical isomers, right? They are asking about it. You must draw the two optical isomers.
Okay.
Show the stereoisomers of compound A, right? That is also expected. And also now since there's carbon and carbon, you can add what? 2,4-DNP also, right? 2,4-dinitrophenyl hydrazine. Remember?
Yeah.
That
But
product
that
was
wouldn't create anything.
yeah, 2,4-DNPH. When you add 2,4-DNPH, what is happening here? Draw the structure of that also. There are many different reactions you can mention. One is enough, but 2,4-DNP.
But with 2,4-DNPH, it doesn't really like make anything. It just shows that there's a carbon.
Yeah, it's a very long structure, right? Can you remember?
I don't really understand what to write for that.
2,4-DNP reaction, can you remember the structure?
The
2,4-DNP.
structure.
Yeah.
I didn't think we ever learned the structure. We just got told about it.
Yeah, so actually when you add 2,4-DNP, it is getting orange color. You don't need to know that structure, right? So you are not, in your syllabus, it is not there, right? It's an orange color precipitate.
Yeah.
Luckily, you don't need to know the structure. I'll tell you the structure, but for your extra knowledge, right?
Yeah.
It's you should remember, right? 2,4 means 2,4 dinitro means 1, 2, 3, 2 and 4 positions are occupied. 2,4 dinitro. Phenylhydrazine means it's something like this. Right? This is 2,4 DNP. Okay, just write the answers, Puta. Draw the structures and write the answers. I'm not going to disturb you.
Mhm.
And as you said, for this carbonyl carbon identification, you can add what? Potassium cyanide to hydrogen cyanide.
Um,
I mean, sodium cyanide H plus or potassium cyanide H plus can be used to identify the ketone one. So that product also you can go, right?
to identify a ketone.
To identify the ketone, yeah. What is happening when you add the sodium cyanide H plus to the ketone? Remember?
I've never learned that reaction. I think because we learned the one where to identify an aldehyde, you add Collins reagent, and if it doesn't show up with anything, then it's a ketone.
Okay, now if you
But
add
I
the
never.
yeah, if you add sodium cyanide H plus, what is happening to ketone? Can you remember?
I don't think I know, but I can try and figure
Yeah,
it
yeah,
out.
give a try. You should know that, right? I'll tell you, but just give a try. It
Okay.
is there, yeah, it is there in your syllabus.
Is that sodium cyanide plus hydrogen?
Very good. Sodium cyanide plus hydrogen. Or you can say potassium cyanide plus H plus. Because we cannot directly put hydrogen cyanide. Hydrogen cyanide is having as HCN is dangerous. It's poisonous gas. So usually we have it as a sodium cyanide or potassium cyanide salt, which is not a poison, just a salt, right? But when we use it, we are putting H plus. So then it becomes a very active poison, hydrogen cyanide, right? So hydrogen cyanide is the active form. So we do not keep it as HCN. We have it as sodium cyanide and acid separately. The moment we add some acid into the sodium cyanide, it is becoming the active poison, right? It is extremely poisonous compound, and it could be even a gas, right? If you had high concentration of H plus, it could get released into a gas, and in some countries hydrogen cyanide is used for, as I remember, for death penalty. Maybe in US they use it for death penalty.
Oh,
So what they do is they have the chamber, they are tying the victim onto a bed. In that chamber what they have is sodium cyanide, and there's a timer, right? When the timer is for example, when the alarm rings, there's a mechanism where H plus is releasing into the sodium cyanide, the potassium cyanide salt containing container. So once the acid is released into the open container, the hydrogen cyanide gas start to release into the chamber, and slowly the victim who's tied onto the bed is getting killed by the hydrogen cyanide poisoning, right? In America, in some states, as I know, they use this mechanism for the as a death penalty, right?
Yeah. Isn't that very inhumane?
It is inhuman, but it's a death penalty, right? So in some state they used even electric chair, right? Even it is all those things are painful. So yeah, it's a
Yeah.
capital punishment. Definitely, it is inhumane. Yeah, it depends. It's a choice of the people in that state, right? So they have voted for that. So yeah,
Yeah.
it,
And so, what property does the hydrogen cyanide has that makes it so dangerous? Like what interaction? You know how carbon monoxide is dangerous because it like binds to your blood vessel. What makes the
yeah,
cyanide so
same.
dangerous?
Yeah, it is still. I, I don't know the exact mechanism, just like for carbon monoxide, but still it is affecting the bloodstream, right? It
Yeah.
is changing the composition of the blood. So that is why most of these lethal uh, compounds that are quickly affecting our body, most of them are affecting our blood. So if the composition of the blood is changed, so the carbon monoxide is also doing something like that. Even hydrogen cyanide also, since it is containing nitrogen compounds, it is suddenly changing the composition of the blood. When the composition of the blood is changed, it is lethal. Same thing with dengue, right? Dengue is also, they are changing the composition of the blood. So that is why it becomes lethal. The dengue fever,
Yeah.
right? So
Yeah.
yeah, so hydrogen cyanide, as I know, it's not a neurotoxin, as I remember, right? I'm not so sure. But I assume it must change the composition of the blood. That is why it is affecting so quickly. Yeah, I did saw a bit of reference. What they say is it blocks the oxygen intake of your blood. It joins through the, it comes through the blood, and in the, if this is our cell, right? In the cell there are cell membranes. So our cell, through the cell membrane, oxygen is taken into the cell, right? So what they
Yeah.
say is because of hydrogen cyanide is blocking the cell's ability to take oxygen into the cell. So as a result, the cells are not getting enough oxygen for the respiration. So therefore, immediate cell death, cellular death. So it means the hydrogen cyanide is affecting this membrane, right? I think they are affecting the protein structure of this membrane. That is why the oxygen is so you know this membrane is a semi-permeable membrane. So the integrity of this membrane must be disturbed by the presence of hydrogen cyanide. As a result, oxygen is not getting diffused into the cell. So therefore, cell is deprived of oxygen. The respiration stops. As a result, cell death happens. Right? Interesting stuff.
Yeah. I think I found the one that I remember.
You
I
found?
haven't actually. Yeah, I just need to draw out both options that I see today.
Yeah, yeah. Just take your time, right? Don't worry. All the questions are going to be like this. So they will change bits and pieces, but same things are being repeated, right? So you must know how to do it right, and with bit of practice you can come out of it, right?
Yeah.
Studying chemistry and answering questions are two different, what do you say, skills, right? Hmm.
I sent it.
Okay. Okay. Looks fine. Mm.
I didn't want a full word as well. I just did
Ah,
it.
that's fine. That's fine. But
How
optical
else?
isomer, it's always use the three-dimensional structures. Otherwise, it's you can't identify it, right? Try to draw the
Um,
three-dimensional structure for the optical isomers.
okay.
3D displayed for always for this for optical isomerism. When they talk about optical isomerism, always sketch the three-dimensional displayed formula, right?
Okay. So it's just two normal lines, a dashed line and a block, isn't it?
Yes, the wedged lines, dotted wedge lines.
Mhm.
So you must learn that because in many marking schemes they offer only marks for the three-dimensional optical isomerism. I, uh, I mean, I mean, for when it comes to optical isomerism, they expect you to draw the three-dimensional displayed formula because with that only it is much more clearer, right? The
Right.
mirror images
So
can
if
be.
hmm, so if I do the three-dimensional one, do I still do the displayed bits for the
Yes, Puta, what?
so if I do it as three-dimensional, do I condense like do I write it as CH2OH or do I still fully like
Yeah, you
make
can
it?
use the hybrid model. You don't need to fully convert into displayed formula, but you must focus on this one, this optical carbon, chiral carbon. So the bonds around the chiral carbon must be three-dimensionally displayed. Right? That is what is they expect. Other ones are not needed, but all the four bonds around the chiral carbon must be sketched three-dimensional, right? Focus on the chiral carbon, right? Other bonds are not necessarily needed in three dimension, right? Only the four bonds around the chiral carbon is expected in the marking scheme. So as a habit, always uh, sketch the three-dimensional display formulas.
Do you want me to send you the 3D way of doing
Yeah, Puta, just send.
it?
Okay. Yeah, there you go. Very good. See, it is very neat and more clearer, and you can also understand it more clearly even for the examiners also. You are doing them a favor, right? Okay.
Yeah.
Right. The question is about amino acids. The general formula of an amino acid is RCHNH2COOH. Most alpha amino acids show optical isomerism. Okay, this is the alpha amino acids. Explain the term optical isomerism. Optical isomerism is when there are two particles okay, that are non-superimposed. Non-superimposable mirror images of each other. Very good. And it happens when there's a chiral carbon. In the presence of a chiral carbon, you get the two compounds uh, that are the non-superimposable mirror images, right? So I don't like the term called particles. What do you think?
Yeah.
Why you mention? Is it a correct term? Having say mentioning about a particle. Why you are calling it a particle? Particle, or shall we call it compound? Isn't
Yeah.
it the more accurate way to tell it? Right? You can say non-superimposable mirror images are having a chiral carbon. I mentioned about that also, right? Non-superimposable mirror images having chiral carbons. Okay? Right. So do not talk it call it a particle, right? Let's say compound. Or let's say non-superimposable mirror images containing chiral centers. It is more complete, right? The amino acids valine has a R group of R group is given. Right? What is the systemic name of valine? Now, first of all, let's draw the structure. You have done that very good. Right. Amide. Now here the thing is it a amide? That is my question. Amide, call it a amide, nitrogen must be connected to the carbonyl carbon, right? Now in amino acids, Okay, is it connected to the carbon and carbon directly? So can you call it an amide? Can you call this an amide?
Um, no.
No, you can't. What are the functional groups it has? How many functions?
An amine and a carboxylic acid.
Okay, amine and the carboxylic acid. Now you must prioritize one functional group over the other, right? And when you prioritize one functional group over the other, the main functional group become the priority. I don't know, you decide which one is becoming the priority, and the second one is becoming just what? Just the substituent group, right? Okay, so substituent group is not considered as a functional group, right? So the substituent
Is
group
the
names can be,
substituent
yes, Puta?
so the substituent group of the amine because
Very
it's
good, very
becoming
good. Substituent groups are names are in the middle of the name, not at the end. The priority group is always at the end. So priority group is the suffix, right? The substituent group, just at the whole structure, it can be part of the middle name or the front name, right? Okay, now can you name them? Now you understood what is the most important thing. You identify the main functional group. Okay, now you can name it now. Now you know how to name end the name, right? The ending is there now. Now just as before, you can name. Can you do that?
I can try, but I probably don't
Yeah.
know.
First of all, identify the main carbon chain and number the carbon chain. First do that. Highlight the or circle the main carbon chain, right? And circle the substituent groups and number the carbons, right? Starting with number 1, you decide whether to number from left to right or right to left, right? Let's see.
Is it 2-amino-butanoic acid?
Can you send me the name to her?
Okay. It's probably wrong.
I don't think. Let's see. I think it's correct. Let's see. You must number them, right?
Yeah.
Two amino. Ah. What about methyl group? You missed out the methyl group, I say, right? Other than that,
Yeah.
you are okay. You methyl group, you have missed. See? Other than that, you are fine, right? And do not leave a space in between. You don't leave any spaces, right? Only on esters. There are some compounds on esters, and when you are naming an acid, then you leave a space. Other than that, we don't leave a space. Keep that in mind. Okay?
Okay.
Right. Can you rename it now? You haven't mentioned about the main methyl group. Methyl substituent group.
Okay. Is it correct then?
Okay, let's check.
Mm.
2-amino. It must be a dash, right? You can't leave a comma. Okay. You don't have. You don't put commas in the organic compounds, right? Except, for example, you put a comma to when you have two numbers. For example, 2 3 2 3 dimethyl. In that case, you put a comma to show in between two numbers, numerical values. You put a comma. Other than that, you don't leave a comma space. It must be a dash. Between a number and a name, it is a dash, right? So it must be 2-amino 3-methyl butanoic acid. Okay.
Okay.
So correct those mistakes. These are very easier to score marks from these.
Yeah.
3D. This is not 3D. Make it 3D. Send it to me. 3D structures. Now in this case, you must make the whole diagram 3D. Right? Make the whole diagram 3D. Try to make it as much as 3-dimensional as possible. So you got to have a good idea about the planes, right? So at least focus on the chiral carbon, and make it 3D. Other parts are not even. If you can do it, that's good. But I think it's kind of too complicated for you, right? So just focus on the chiral carbon and make it 3D, right? Other parts are not necessary needed.
I sent it to you.
Well done. Huh? Three amino acids react together to form compound E. Uh, we have done something similar to this, right? I guess
Yeah.
we have done this,
I
I guess.
wasn't sure if I did the splitting quite correctly though.
Yeah, let's see. Amino acid E. It is getting broken from here, getting broken from here. Okay.
Then I found 4 chiral centers.
4 chiral centers, 2 to the power of 4, 16. Very good. Yeah.
Is my addition of the H's correct?
Be careful now here. Nitrogen can have only up to. So, what did you mention by another hydrogen put? Protonated, right? In the
Isn't
presence
there
of
lots
H.
of
Yes, very good. But you should must
hydrogen?
put the H plus, right? Once it is protonated, you must mention it as what? H plus NH ammonium ions, right? See, these are.
Uh,
It must get protonated, so it gets what? Plus charge. Okay. Understood, Putta?
yeah. So, even though it was only NH to begin with, does it matter if it's now NH3 to begin with?
So if you are leaving it as NH2,
Because it's only NH to begin with, so do I make it an NH2 or an NH3?
if it is NH2, it doesn't get up. Usually, it is getting protonated in the presence of H plus, right? So if you have excess H plus, usually it is becoming NH3 plus, right? It is getting additional hydrogen, NH3 plus. Got it? Understood? Hello?
Yes.
But remember now in the marking schemes, in many usually if you either you put this one also, you will get marks, because to have to get this protonated, it must be there must be excess H pluses, right? So we are not so sure whether they have excess H pluses or not. So both the answers are usually accepted, right? NH3 plus or NH2, right? But if it is getting protonated, you must plus the positive sign and don't put an arrow, right? It is a normal covalent bond. Once the bond is formed, it is acting as a normal covalent bond. Okay? But you must mention the charge. Understood?
Yeah.
Now the question is about unsaturated hydrocarbons. B and C are branch hydrocarbons that are structural isomers. C6 branch hydrocarbons. Okay. B and C are both have stereoisomers. Okay. B has a cis and trans isomer but does not have optical isomers. Okay. C has optical isomer but does not have cis trans isomers. Right. Now it's a very good one. C6H12. Now they say it's a hydrocarbon. What could possibly this be? Alkane or alkene?
An alkene?
Yeah, it's an alkene. I'll give you a small hint. Alkene. So this alkene, right? Now alkene must be the B, right? Because it contains cis trans isomer. Then can't this be alkane also? What do you think?
And does it have enough carbons and hydrogens to be an alkane?
If it is
Because doesn't
cyclic, if it
it
is,
CmH2n plus 2?
yeah, but if it is a cyclic alkane, still this number of carbons and hydrogens are fulfilled. Be careful, right? Sometimes there
But
are cyclic
this
alkanes.
is hydrocarbon.
Yeah, sometimes there are cyclic hydrocarbons, right? If it is cyclic, this number of carbons and hydrogens are still fulfilled. There are cyclic alkanes. Cyclic
So can this one still class as bran? Because it says bran.
yeah,
Remember that
yeah, you
before?
can make it now. There are 6 carbons now. It doesn't necessarily need to be the whole 6 carbon series branch. Maybe something like this, right? Maybe 3 carbons are being branched or cyclic. So you have to think of that option also. Maybe it is cyclic. Who knows? Right? They are branched hydrocarbons, but who knows? But we don't know whether they are branched or not. And the question is about unsaturated hydrocarbons. So therefore both must be alkenes, right? Can't be cyclic. Both are alkenes. Unsaturated hydrocarbons, no. Unsaturated hydrocarbon means there must be double bond. So from that point we can tell it is not cut, non-cyclic. Both are non-cyclic. Sometimes there can be cyclic ones also. Now we are so sure it is not cyclic, it is an alkene. One is an alkane, it is cis trans.
Can't the alkene also be cyclic?
This one is also this is not a cis trans isomer. Alkene, but it is not cis trans but optical isomer. Optical means it must contain a.
I'm kind of about the branch cyclic definition.
No, don't worry. Right? Forget about being branched. Now they are helping us to find the structure, that's all. Now you must be very careful. Now forget about this branchness. Can you come up with a now first one is what is the structural isomer? What is the structural isomer? You can answer this part now. What does it mean? What is the structural isomer? Yeah, Puta?
The structural isomer is like it has the same molecular formula but occupies different.
Yeah, different structures, right? Compounds having same molecular formula but different structures, right? Stereoisomers, what do you think? What do you think?
When it's on the same side of the opposite side.
Stereoisomers have the same structures. So structural isomers having different connectivity or different spatial arrangement, right? In 3-dimensional space. Be careful when you are defining them. Same structural isomers having different spatial arrangement or the different connectivity in the space. That is called stereoisomer. Okay. Now these are easy stuff. Can you identify? Let's forget about other stuff. Shall we identify these three? What is B and what is C? Can you come up with a structure for B? It must be a cis trans isomer. So remember, it's like swimming, right? So you can't learn swimming by being on the land. You got to try it. That's an age of organic chemistry. So at the by looking at it, you actually, for me myself also, I can't actually figure it out. But what I do is I take my pencil and I start sketching few and see whether it works, right? So that's the nature in organic chemistry. That is why we should write and draw structures, draw diagrams. It is like being a swimmer, right? We can't learn on land, no matter how many classes we take for a swimming. We must be on that in the deep end first. Then only we learn how to swim. Same as here also. Yeah, let's sketch a structure and see whether it works. Can you do it?
Yeah.
Yeah, give a try. Not that hard. Be creative, huh? Be creative.
I think I did it.
Okay.
I'm not really sure.
I see. Um, did you send it to me? Send me a picture of that.
Oh, okay.
Okay. Mm, optical isomer. Okay, now the thing is, in your answer, I'll tell you, if you are talking about a cis-trans isomer, these are the conditions. If this is the double bond, if same groups are connected to two carbons, same group, can you call it a cis-trans? What do you think? For example, I'll call hydrogen here, hydrogen here, hydrogen here. Is it cis or trans?
I'm not sure.
No, you can't. Right here, it is not a cis trans isomer, right? For example, now you are calling this one the trans of this. For example, this time I am taking CH3 here, hydrogen here. It's the same structure, right? To the carbon double bonded, so for the at the carbon containing two double bonds, similar groups are connected. It is not a cis trans isomer, right? No. Understood?
Yeah.
Now in one of
That
your
one I about anyway.
yes, Puta?
That one was the one I was unsure about, but I think I got compound.
Okay,
Yeah.
now it is not a now if you have connected two different ones, then it is fine. Let's see. Okay, that's optical one. Very good. Sure. Uh, let me check. See, now you will have to, now there's a small error in that, right? Okay, now which one is the cis trans isomer? Okay, good. Uh,
Because it says compound C doesn't have cis trans isomers but has optical isomers.
okay, optical isomer is okay. C answer is okay. You are fine. B answer.
Yeah, I just didn't really figure out compound. Oh yeah, sorry. I think I labeled it wrong. I was supposed to be compound B.
Yeah, compound B.
labeled.
Yeah, compound B. Compound B. Compound C, right? Your compound C is okay. labeled it. Okay, what is compound B then? Can you figure it out?
I'm not really sure. I got really stuck in that.
Give a try, give a try. You can you place the double bonds here and there, make it branched and see. As long as you get similar groups in the opposing carbons, that's fine, right? You must get similar groups, right, in the opposing carbons. So that makes a cis trans isomer. Come up with a structure, you can do it.
So I just can't. Does it have to be 4 different groups then?
Not 4 different groups, 2 different. No, you can't have 4 different groups, no, because it's an alkene. No, you can have only 3 groups attached. Forget about 4 different groups. For 4 different groups are for optical isomer. For cis trans isomer, focus on the double bond, right?
So what's the error in the one that I've currently got?
Did you send me an answer for C, Puta? Answer for B?
Yeah, I just accidentally labelled it C. The one in blue at the top is supposed to be for compound B, not for compound C. The one at the bottom is compound B.
No, you can't, right? Why I am saying so? So I can't see the B no label. Below one, is it?
No, so the below one is compound C in yellow, but the stuff in blue that I've done is compound C. Well, I'll just send it to you again. Actually.
Yeah, but here there's a small issue. Look at the double carbon double bond, right? In the carbon double bond, I told you this carbon must not have similar groups attached. It must be 2 different groups, 1 and 2. Now in your structure, same groups are attached. No, it must be different groups. Similar groups must be attached to opposing carbons. Now here it is okay. Now it is fine. Then it is cis trans, right? Understood? I will make it clearer for you. Okay, look at here, Buddha. See, carbon. To make it cis trans, it must be like this, right? Now this is okay, but in this case, this is not cis trans, right? See, because of this reason, it is not cis trans. Similar groups cannot be attached. Understood?
Yeah.
Yeah. Now, why don't you try to bring the double bond somewhere else? Another thing is, in your structure, there is an optical carbon. So that is why it is definitely wrong. Why? In your second structure, compound C, you can't have a optical carbon.
But it says compound C has optical isomer.
That's okay, but the compound B is can't have, no. What you are saying is compound B is yeah, the blue color one cannot have a optical carbon. So that is why therefore it is wrong, right? Can you sketch both near each other and label it clearly, right?
And where would the optical carbon be?
It doesn't have optical carbon, right?
Yeah, so you're saying that my structure has, where is...
I'll show you, I'll show. Right. So here in your answer, now you are saying this is compound B, right? Isn't it?
No, that's compound.
C. You are saying it is compound C. This is compound B.
No, that's just compound C and 3D.
Okay, so where's compound B then?
It's the blue one at the top.
This one.
No.
Okay. Then what?
One that's labeled with a box.
This one.
No, there's a box around it. If you zoom out a little bit.
Yeah, I couldn't see it now. Not it is not saying.
You're a bit zoomed in. If you zoom out a little bit, it should be there.
Okay. Where is it?
I put it as compound C by accident.
Can you send it to me again? Yeah, I don't see it clearly.
It's the one that I've drawn a square in, but I'll send it again.
Yeah, can you send it to me again? Yeah. Let me check.
I'll send it.
Okay. Yeah, that's correct. Good. So that's compound B, and you just name it. That's its trans. Yeah, that's correct. Okay, good. See, now you told me you don't understand it. You got it, huh? You got it right without any help. See, I told you, you got to swim, right? And you got to be on the pool. You got to be on the deep end. You must be thrown into the deep end, right? Otherwise, by just looking at the answer, you can't figure it out. For anyone, even for me, even for an expert, right? Just give a try. Use your pen and pencil, work it out. It's very interesting, right? Just by looking at the paper, we can't get the answers. This is science, I told you, right? You just have to work it out logically. You have to sketch, and it's very interesting. I mean, when you get an answer correct, right? Because we are working on that, and you are logically approaching an answer, right? So there's a bit of it's kind of like a small treat, at the end of the journey, right? Other than just memorizing and writing a stuff, because we have worked for it. Very good job. Though the structures of cis and trans isomers, branch cytocarbon. See, I told you. Now you were worrying about being branched. I told you to forget about being branched, right? Automatically in your structure it is branched. See, you have made it out. Okay. Right. For this one, you need the data booklet, right? Okay, no need. No, this is proton NMR, cetan NMR, IRP. Compound DNA, the structural isomer, 6. Okay. Two more structural isomers.
What question are you on?
Yes, Puta?
Which question are we on?
We are in the 5th one, right?
Oh, okay.
These things we are done. No? Compound B and C we are determined. No? Right?
Yeah.
Compound E have more structural isomers. This means now a different one, not the one that we have done, right? They do not show optical isomers or stereoisomerism. So no geometric or optical. So the NMR and IR spectra of the data DNA. Number of peaks in proton NMR spectrum. Number of peaks in C30 IRs peak at 1620 and 1680. No and yes, right? What does it mean? 1620 and 1680. This peak is for what? Do you have the data booklet?
Yeah, I do.
Check and tell now.
1680 is a carbon-carbon double bond for alkenes.
Okay. Okay. What is the functional group? I couldn't hear you.
Alkene.
Alkene.
Yeah.
Uh, it means it's an alkene, but it does not show stereoisomerism,
Yeah.
right? So now we are getting a small hint. It doesn't show optical isomerism even, right? One is it's an alkene, okay. Other one, what they say is no IR peak. What does it mean? One is an alkene. It means this is an
What
alkene.
is not?
Yeah. Then what does it mean? There's no alkene group. What does it mean? If it is not an alkene, what do they mean?
They just mean it's not an alkene.
It's not an alkene. So it means, but it must have same molecular formula. It can be cyclic, I guess, right?
Yeah.
Yeah. So we can assume, right? We are just assuming, right? Just like Sherlock Holmes, right? You can call it like cyclic. Isn't this interesting, right? Okay.
Mm.
Yeah, that will make sense. Number of peaks of C13 NMR spectrum. One is saying 2, one is saying 1 and 2.
Yeah.
Yeah, what does it mean? Number of carbons. It means,
Like unique carbon environment.
yeah, very good. There's only one carbon environment. So it must be symmetric, right?
Yeah.
It must be symmetric molecule having one carbon environment. Very good. There you go. Here you have only two different carbon environments. Two different environment. And these are the evidences that this must be cyclic. And you have only a symmetric molecule. This one is, there's only two different carbons, and it is an alkene. Now you should be able to figure it out. Let's see. Shall we? Can you give a try?
Yeah, I can try.
See.
So it puts one peak in the H NMR. What does that mean again?
Excuse me, Puta?
You know how it says there's like 2 peaks for 1 peak in the carbon NMR, and then it says both of them only have 1 peak in the H NMR.
Yeah, so it means when you look at the number of hydrogen, it also there's only one hydrogen. So it means there's only what? One type of hydrogen is there. One type of
Okay.
hydrogen.
But the peak could be in like 2 completely different places.
Yeah, just like carbons. There can be 6 carbons. There must be 6 carbons. There must be 12 hydrogens. But they all must be detected as the same hydrogen, because computer doesn't know, right, whether this carbon is situated somewhere else. As long as the environment is the same, the computer is detected as all together as one hydrogen or one carbon, right? Computer only detects it as long as the environment is the same, even though there are two different carbons or hydrogens, they are detecting it as the same hydrogen or carbon, right?
So compound.
D1 is easy, yeah, give it a try. D is easy, not that hard, I guess.
Oh, okay. I thought D was a bit harder because at least with E I know it's an alkene, so then one of the environments will be a carbon-carbon double bond, and the other carbon environments will be just normal carbon hydrogen.
Yeah, just try both. That's good, right? Consider everything. So one is cyclic, D is cyclic, no alkene group, symmetric molecule.
I made that I think could be compound. It is symmetrical, but it could be wrong. But I think there are two carbon environments because there's a double bond. But I'll just send it to you.
Yeah, there are two carbons. Yeah, it's kind of like a small puzzle, right? Yet how can we think of it now? If that contains a double bond,
I said what I think it could be.
we'll see.
Kind of symmetrical.
Let us
It's got two different carbon environments.
There
But
are
because it's
there are
CH3,
there
it would
are
have more
uh,
than a H element.
so there are three different carbons, right? Isn't it?
Yeah.
And when you
CH.
yeah, and hydrogens are also there are how many different hydrogens? 1, 2, 3, three different hydrogens. Okay, give a try for D. It's straightforward, I guess. For D, it is straightforward. Symmetric cyclic compound. Just see.
Oh. Yeah.
D is easy. Okay. I figured out E also. By looking at your answer, I figured it out. Let's see whether you can do it. E. You just need to
I
do
figured out this cyclohexane, isn't it?
Yeah, cyclohexane. E. Focus on your on your structure E. You will have to do few changes.
I've got rid of it all, so I'll just start again.
Look at E. You're almost there. You're almost there. You just need to do few changes only. Few changes. It's a very interesting question, huh?
So it's an alkene. Is this one also cyclical?
No, can't be cyclic. It's an alkene. You are almost there. Why can't you think of branching it? There are tertiary. You can have,
Because I can't figure out a way so that there's only two different carbon environments.
Can't you connect directly connect carbons, two carbons to that carbon containing double bonds? Rather than having a long tail, can't you connect the two carbons separately directly to the carbon containing double bond?
Oh.
Just let's see whether you can do it. We are just doing some assumptions, right? Maybe it is right, correct, right? So it's nothing hard. You need one thing is you need bit of luck, right? Bit of luck is needed, and other thing is practice, right? In organic chemistry you need bit of luck sometimes. That's why I'm telling you not to waste your time. Do not hang on to a question, right? If you're lucky, sometimes you might get you must do a guess. Sometimes it may work, sometimes it may not work, right? So do not hang in on there, just skip and do other questions. Sometimes by the time you come back, when you do your next assumption, maybe second time you may be lucky, right? Just have to give some lucky guesses, right? Especially in organic chemistry. So a bit of blessing is needed actually, right?
Yeah. I sent it.
Okay. There you go, right? It fulfills everything, right? Good. Yeah, simple as that. Not that hard, right? But we need a bit of luck, that's it. Okay. So don't get discouraged as long as you are, because you did this, not me, right? Yourself you did. I just guided you
Yeah, I was
through.
trying to get compound in. But
Yeah, compounding. Yeah. Yeah, that's okay. But next, another thing is, please, your compounds, your diagram must be more clearer. Now remember what I see is between the carbons you are mentioning only very short dashes like this, but it must be connected at least like this, right? So it must be, the diagram must be much bigger and more clearer. You might, it's a disadvantage for you, right? At least the way I do it, right, must be a bit more clearer, and these dashes must be, carbon must be, these bonds must be much longer, right? So otherwise they might consider cutting marks, right? So we must consider everything, right?
okay.
About that.
I'll redraw it.
Yes, Puta, I couldn't hear you. What
I'll redraw it.
are we?
I will redraw it.
Yeah, yeah, can you do draw it and send it to me?
Send it. Is that Does the new version okay?
Yes, Putra?
I sent a redrawn version of.
Ah, that's great. Good, good, good. Much better.
Is it better?
Much better, right? Try to, increase the length of the bonds, right? So, yeah, much better, much better, right? Good. Uh, shall we continue next week, Putra? What do you say?
Okay, so
Okay.
did you want me to
Yeah,
try with the question?
sure, sure. Hello?
Okay.
Yeah, you have question?
Um, no, I was saying, did you want me to try the rest of the questions
Yeah,
before
please.
next
Yeah,
time?
yeah. Please complete the other rest of the questions, right? Then we can next day we can discuss them at the class. Okay.
Yeah. Okay.
Take care. Bye. Okay.
Okay.
Yeah. Sure. And
Yes.
I think there's a small delay in the what do you say, the payments and everything. That's fine.
Yeah,
Uh,
I'll make sure that I'm not
yeah. Yeah. That's fine. Okay. Sure, sure. Take care. Bye. Bye. Stay safe. Right. I hope things are okay in UK these days with the war going on in the Middle East and all. So,
Yeah.
yeah, okay, okay. Take care. Bye bye. Stay safe. Okay.
For now. Okay.
Bye bye.
Thank you, bye.
See you. Take care. Bye. මොකක්ද? සතුටු වෙ යකෝ ගෑණි වුණාම සතුටු වෙන්න බෑ. shopping ගියාට කවන්න නැහැ මෙච්චර ගාන එකතු කරන්නේ. මොකද? ඇයි? ඇයි ඔය කොහොමද වාට මගේ සල්ලි තමයි තියන් ඉන්නේ. වෙන එන උන් උත්තර සල්ලි තියන් ඉන්නේ. හා? හා? මගේ සල්ලි තමයි තියන්. නෑ නෑ මම උත්තර දෙන්න මං අහපු උත්තර දෙන්න. දැන් කවුද මට ටම් ක්ලාස් කරන්නේ? මම දන්නවා කවුද නේද කියන්නේ කියලා. දන්නවා. මට වඩා හොඳට උගන්වන්න පුළුවන් ඇති කොළඹ කැම්පස් එකේ. හ්ම්. දැන් ආවනේ පළතුරු මොනවද ගන්න අනාසික දෙයක් කරගන්නේ කොච්චරද ඊට වඩා. හ්ම්. එයි. මේ බබා මං අර මුකුත් ක්‍රැක් කරන්නේ අර ගොල්ලන්ගේ අර මේ නිසිනිගේ යාළුවගේ ඒවා නිසිනිගේ යාළුවා ඉන්නේ අර අරක උන් සල්ලි ගෙවලා නේද ඉන්නේ. පැය ගණන් මුකුත් මන් දන්නේ නැහැ ඒක ක්‍රැක් කරන්නේ නැහැ ඒකවත්. ඒ 10000 මොකද්ද? 10000 මොකද්ද? 8000 දෙකක්. අම්මට සිරි. බයෝ එකයි දෙකක් නේ. හරි මේ මට පේනවා මේ අම්මෝ ආ මට ගේම් තියන්නේ නෑනේ අම්මෝ අහිංසක මලක් නංගිට තරහා යනවා නම් දන්නේ නෑ මංගේ සකිට ගාතේ වලියක් ගියා උන් ආව තුවක්කු දික් කරගෙන ඉන්නවා දැක්ක ඇරින්නේ මොකක්ද හරි මම කිව්වා මම දන්නේ නැහැ කියලා පැය කීයක් කරන්න දරකද කියලා මම ට්‍රැක් කරන්න බෑ කියපු ඒකයි උඹ 10ක් දෙන්න එකයි තුනයි හතරයි සික්කිය දෙකයි 3යි 4යි 5යි 6යි 7යි 9යි ස්ලිප් 9ක් තියෙනවා 9යි කියන්නේ 10 ගානේ ගත්තොත් 9 10යි මාර්ග හගත්තොත් 20යි ඉතින් බලන්න බබා මොකක්ද අනේ බබා ඉස්සරහ දින යන්නකෝ එයි ඉස්සරද කොහොමද Yes, Puta. Where did we stop? Hello? Hello, where did we stop? Hello? Can you hear me?
So what paper is that a paper?
Did I share something with you?
Yeah, I think we finished that.
Oh yeah, we have finished the paper, right? I think we have shall I send you a paper?
Oh, okay, sir.
Give me a second. We'll focus on the full paper, I guess. That's better. Your paper code is 0971, is it? Can you tell me your paper code, Puta?
No, sir.
It's
I think it's 0570.
0570.
5070.
Yeah, 507.
570. We'll start off with this paper. I'll upload in the group. Okay, we'll move on to MCQ one, I guess. Let's get that. I think we have done the 2024 paper, I guess. Yeah, 2024 paper. Yeah, I'll send you this. Right. Can you finish all this paper quickly, right? It's a MCQ one. Finish as fast as possible. Like within about 40 minutes, just see. It's a 1 hour paper. Yeah, it's a 1 hour paper. Let's see whether you can do it.
Sir, did we finish organic chemistry?
As I remember, we have completed, but I am not so sure. So that's why I was wondering. Did we? Where did we stop?
We stopped at hydration and fermentation.
Hydration and fermentation. Hydration and fermentation is
The
on.
differences.
Let me check. So I think still we are under this hydration and fermentation. So it is on alkenes, I guess, right?
Yeah, no, alcohols.
Alcohols. Okay, production of alcohols, right? Yeah. I think we are almost done. Let me check. Yeah, I think we are almost done. Carboxylic acid did we do?
No, sir, we didn't do
We
carboxylic
done
acid.
it. We'll finish it off first. And even I was wondering, I felt like whether it is over or not. So studied chemistry. Alcohols we are done. We have to have carboxylic acid and then finally polymers. Right. We are in now. So we have started it off, right? Carboxylic acid. Carboxylic acids. So under carboxylic acid we have the introduction, and then ethanoic acid, then esterification reactions. And esterification reactions. Then okay, let's move on to directly to carboxylic acids. Right. Now carboxylic acid, actually it's a weak acid, remember, weak acid as the name says, right? And carboxylic with metals, reacting with metals, what does it give? Just like an acid. I will give you the reaction and you just write the products, right? Let's say CH3COOH with magnesium. Write the products. And other one is reacting with carbonates. Now you should know, reacting with carbonates. Let's say sodium carbonate. Write the products. And reacting with right bases, with this sodium hydroxide. Write down the products. Send me the answers. Let's see whether you can remember this. Okay.
Yes, sir.
I haven't received your answers yet. Mm. Very good. Okay. Very good. Right. Now remember, in all these cases, salt is one product. In all these cases, acid salt is made, right? And but the other thing is, in here, only in this case we get the water released, right? Here we got the hydrogen gas released, and here carbon dioxide gas released. Okay.
So in the
Displacement.
what the second one?
Yeah.
Water releases with
No
carbon.
water is released. Only water is released at the acid base reaction. So therefore, only this reaction can be considered as a neutralization reaction. Most of the time students are getting this wrong, right?
So then, what happens to the hydrogen?
Hydrogen is displaced.
In the
First
so,
term.
as in the reacting with carbonates,
Yeah.
now sodium replaces hydrogen. So what happens to the hydrogen and the extra oxygen from the carbonate?
Yeah. So you are getting the salt, carbon dioxide. What else is released? Yeah, definitely water is there. Yeah, water is there. Right. So this is also acid base reaction, right? Sodium carbonate is a base. Now remember, this sodium carbonate reaction and the other normal acid base reaction, these are only what? Neutralization reactions, right? Only these two can be considered as neutralizations. Why? In the neutralization reactions, you must get the metal salt plus water must be there. Metal salt and water both are not there in the equation as the product, you can't call it a neutralization reaction. Most of the time students are getting this fact wrong. So remember, yes, you are getting the metal salt, but since there's no water released, due to the absence of water, we do not call it as a neutralization reaction, right? No neutralization reaction. Okay, understood.
Yes, sir.
Right. So keep that in mind. It looks like a neutralization reaction, but we do not call it as a neutralization, acid-base neutralization reaction, right? Right. Now remember, in the acid-base reaction, the salt of this acid is called what? For example, CH3 COO minus Na. So what is the name of this? Can you tell me, one of you tell me the name of this? What is the name of the salt? Scientific name? Any one of you know?
It is sodium acid.
Acetate is not the scientific name. IUPAC name?
No.
No,
Is
it's
it
just a
sodium ethanoate?
very good ethanoate, right? Sodium space, now space ethanoate. Why ethane? There are two carbons, ethane, and remember now ethanoic acid. Now since it is derived from the oic acid, ethanoic acid, we do not call it oic acid. It is getting cancelled off. We call it what? Ethane O8. Oic acid, oic is removed with what? O8. All the time the name ends with O8. For example, write the name of this. Okay. Write the name. What is the name? answer though. Hello?
Sir, I'm not able to send the picture on the group.
Yeah, what's the name then?
Can I just say the answer?
Sure, sure.
I came up with magnesium pentanoate.
Magnesium 1, 2, 3, 4, 5. Magnesium pentanoate. Very good. Yeah, that's the name. Okay. Now let's move on to esterification. Those are the reactions of carboxylic acid. Then write ethanoic acid, then esterification reactions. And esterification reactions. Right? Formation of ethanoic acids. Ethanoic acids. You can do it in two ways. One way is oxidation. Now oxidation is done through a natural process called fermentation. And the other method is oxidizing agents. Now, usually what they do is alcohol oxidation is used. Now, this is the reaction. Now, you need an alcohol. So, now we are trying to make ethanoic acid. So, what we need to use is ethanol in the presence of oxidizing. Right? We are using a catalyst. Right? Write the products for this. Right? So usually this process is a natural one. This is called microbial oxidation. Microbial oxidation is used. Right? What is the product? What are the products? You are producing ethanoic acid, CH3COOH plus water. Now this is usually vinegar is what? Ethanoic acid. Vinegar. Right? Now remember, same thing happens in the production of wine. Now depends on the, you get a different flavor in different alcohols. Now for example, in the grape juice contains ethanol, and when it is being exposed to the oxygen in the atmosphere, in the wine itself, it contains what? Acetobacter bacteria. Acetobacter. Bacteria contains certain enzymes, and it gives what? Wine. Now wine is also at ethanol, right? Wine is also ethanol, but it contains a different flavor. By remember, because in the juice of wine it contains other chemicals also. So once vinegar is mixed with other chemicals in the juice, we call it wine, right? Okay. So that is why different using different food, you can make different alcohol containing different tastes, right? So actually the alcohol part is the same, but it gives a different vibe, it gives a different taste because of the presence of other chemicals, other compounds, right? Sake, it contains a different vibe, and whiskey is in for example Scottish whiskey, and also you have a vodka in the Russia vodka, right? In Sri Lanka also different name, Kasipu, whatever it is, right? So now in the juices, because of the other contains other chemicals, when other chemicals in the juices of different plant-based products, when these juices are getting mixed with the alcohol, it gives a different flavor, right? But the main compound is alcohol. That is what is actually making us high, right? You must have heard. Now there are different cocktails, right? So now they are mixing alcohol with different different juices, and they make different cocktails, right? So but still the main ingredient that is causing that highness is alcohol, ethanol, right? Okay. Now scientifically, right, we can show it in a shortened way. Ethanol is this CH3 CH2OH aqueous with oxygen, oxidized. So instead of writing oxygen, we can put this signature, right? It is called an oxidizing agent. So since it is getting only one oxygen, it is the product, right? This is the shortened way of writing it. This oxidizing agent can be anything, right? Okay. Now remember the oxidizing agents when we do it industrially, right? You can use different oxidizing agents. Example, potassium manganate, right? One example. So that is how we write. This is what we example for oxidizing agent, right? Now remember, when you make this industrially, you are making ethanol into ethanoic acid. But remember, now we have other compounds. Water is also there. Remaining ethanol is also there, right? Okay. Now we have to find a way to separate this ethanoic acid, right? So how do we separate this ethanoic acid? Must be separated. Can someone of you tell me, right? How to separate ethanoic acid? Hello?
Fractional distillation.
Fractional distillation, right? Because now these compounds, other water has a different boiling point. Ethanoic acid is having a different boiling point. Remaining ethanol is having a different boiling point. Potassium permanganate. So all these are containing in our product now, right? But we have to make sure we have to find a, we should separate it, and we should get a more pure product, right? So fractional distillation is the method to go, right? Pure ethanoic acid is separated by distillation, right? Keep that in mind.
So is it fractional distillation or just distillation?
Simple distillation is enough, right? Fractional distillation is not needed. Fractional distillation is used mainly for example, crude oil. If you have a mixture of compounds having different boiling point, melting point, then you need to have a fractional distillation, right? Simple distillation is more or less is enough. Now remember, in the process of making this, in the production of ethanoic acid, when ethanoic acid is produced, right, a reflux method must be used, right? Now after ethanoic acid is made, through distillation you can separate it. But in the process of making ethanoic acid, to make sure you are getting a better yield, right, a reflux method is used. Have you heard about reflux? Heard about it? Hello?
No, sir.
Right, reflux is similar to distillation, but the only thing is, now it's like this. Reflux is something similar to, have you heard something called a pressure cooker in cooking? So
Yes, sir.
yeah, in the pressure cooker you are keeping the lid closed, right? So here also what we do is, in the distillation we let the separated compounds leave the mixture, right? Because what we do is we are separate the compounds that we need to separate into gaseous state, and by condensing them we can separate it, right? But in this case we need to make sure we are getting a better yield. You should make sure, right? The reaction is moving forward. We are getting a better yield. So we should make sure almost all the ethanol is converted to ethanoic acid. So therefore, to make sure it is happening properly, there is a method called chemically reflux. In the reflux is something similar to distillation, but the only difference is in the distillation compounds are separated, but here we don't separate it. What is being separated as steam again being poured back into the mixture, right? For example, this is the cross section of this reflux diagram, right? Usually in our labs, in your labs you don't find this, you find this usually in the university labs. This is called a refluxing column. It is like a distillation column, right? Now only difference is, right, this is the tube, this is the there's a tube, and here we have the mixture, and this is the water bath. Now in the water bath we have what? Heating. Now here we have the reactants. Reactant means ethanol plus oxidizing agent, right, at the beginning. Now what happens here is, now the reaction is happening and you are heating it. Now several compounds are being separated and going up as a gas, right? Now this is the gas phase. Now in these gases you have ethanol, oxidizing agent, and also what? Ethanoic acid, right? Now what we do is we want to what? Bring it back to the mixture, right? So what we do is, just like in distillation we have this column here, there are two ends. We are sending water in, water out, right? Water out. So all this gas mixture containing, we are talking about the gas mixture, it doesn't only contain ethanol and it doesn't only contain ethanoic acid, it contains everything. All the mixtures are again being condensed and again falling back into the mixture, right? Likewise, several cycles are going on. The reason is, right, when they are in the gas phase, temperature is much more higher than your liquid, right? You know, steam is water you can boil on only up to 100 centigrades, pure water. But steam, it can go up to any temperature, right? It can go up to in 500 centigrades. So that is why if your hands are getting burned in boiling water, damage is relatively less compared to steam, right? If your hands are getting burned by steam, most of the time the damage is permanent, right? That is why sometimes even when cooking, steam is used. You know, there are steamers. When vegetables and everything are boiled, sometimes they are using a steamer. Here you have water, and the water gas is what? Used for this, steaming. Because the temperature of the steam is much greater than 100 degrees centigrades. But in boiling water, you can only boil up to 100 centigrades. But in steam can go up to beyond that levels, right? So just like that, you are boiling it, it is becoming a gas, and this gas phase you have higher temperatures. So therefore, reaction is happening more efficiently at very high temperatures, right? But the thing is, now we have to bring it back to a solution. Therefore, what we do is we are cooling it down. So all the steam is going up, again coming back, again gets heated, again coming back. So therefore there are several refluxes. We are calling them refluxes cycles, right? Reflux cycles. there are several cycles. Once several cycles are going on, now we know it gives a very good, a better yield, right? Once the several cycles are going on, we know you are getting a better yield, right? Now when you do this experiment at lab, you can see the steam is going up, getting condensed, and again floating back, again going up, again floating back. Likewise, this condensing tube, right? It's a very interesting tube. The cross section, this is a transparent tube, right? This is a glass chamber. This glass chamber is transparent, so we can see the gases going up, getting condensed. So there are some droplets are again falling down. You can see it's happening. So we can see several phases are going on. So that all those things are happening inside this inner tube, inner chamber. Outside chamber, we are sending water in. Why? Because we want to condense this steam, and again this condensed water liquids or the liquid phase reactants and the products are again coming back. So that is this process is called reflux, right? Here at the bottom we have what? Heating source. Understood? Hello?
Yes, sir.
Right. So this is called refluxive, right? This refluxive method is used to get a better yield of ethanoic acid, right? Once ethanoic acid is made, then later you can use what? The distillation column, distillation process to get a pure compound, right? Okay. This is called reflux. Okay. So remember, in this mixture you have ethanol, oxidizing agent, and what? Ethanoic acid, and also water. Whole mixture is there, right? Rotating around like a water cycle. Several cycles are going on. Once several cycles are done, we know we are having a better yield, right? Okay, this is called reflux. Okay, you can see watch some YouTube videos, right? So when you type refluxing, it's there, right? Okay. Right. Let's do few questions on this. Then we have only we are only having polymers. With that we are done. Right. Before that we'll do few questions. Right. Okay. Organic chemistry. Carboxylic acid. Right. I will send them in the video. Can you do this question MCQs? It won't take much time. Hello, can you hear me, guys?
Yes, sir.